So in this video I'm going to continue with the grade 9 ASP practice questions, and you're probably going to get sick of graphs by the end of it, but yes, we have more graphing things to do. So let's have a look. In this one now we're moving to a position time graph. Before we did the velocity time graphs, now we're looking at the position time. So you need to know what happens to the position in different cases. We will go through them all. So first here, position time. My position is constant. I am not changing my position. What does that mean? It basically means I am not moving. My position remains the same after a certain amount of time. I am at rest. So this is at rest, not moving at all. So you can see here it says uniform non-zero velocity. He does not have a velocity. It's a trick. You might think a horizontal line means constant speed because the previous graph, it was a speed time graph. No, he has a constant distance, meaning he is not changing his distance. That's why that's wrong. Let's look at B. Now, looking at B, his distance is increasing as it was about. That was a terrible line. I'm not going to draw it. But yes, his distance is getting further as time goes on. B is making a constant change. I said I'm not going to do it, and I did it again, and I made the same stupid mistake. Let's cancel that. What am I saying? Yes, he is speeding, but he is not speeding up. He has a speed, but it is not increasing. How am I supposed to know this? Well, I did show you the different graphs. 1, 2, and 3. This is xt, vt, and at. If I had a constant speed, I am increasing my speed at a constant rate, by increasing my distance at a constant rate. The slope of a position graph, rise over run, look at this, x divided by t, rise over run. Rise over run, that's v. Right? V is distance divided by time, or displacement divided by time. This means I have a constant speed. If I have a constant speed, I have zero acceleration. That's how they're linked. So the slope of the position graph will tell me the speed. And then, if that is a constant speed, I have no acceleration. So B having positive acceleration is wrong because his distance graph looks like this. Let's look at C. Now, C has a little speed here. He is going from this place back to here. You might think it's slowing down, but actually, no. It is a constant speed. It is a constant negative speed. So it's the opposite of this. So if I was to draw it out, it's looking like this. And if I was to do the graph for it, this will give me a negative gradient. So it'll be on the negative side, constant. Constant is a straight line, so there'll be a constant. And then, of course, acceleration, if it is a constant speed, that's t there. If this is a constant speed, my acceleration will just remain at zero. There will be nothing again. So C is not slowing down because it is not changing its speed. It is a constant negative speed, which is represented by the graph looking like this. Finally, D accelerating, yes. If D is accelerating, you will get a curve. That is true. That means my velocity graph would be increasing like this. If this is my velocity graph increasing, my distance graph must be curving upwards. Why does that make sense? Let's find out why. After a certain time, I have a certain speed, so I will go a little bit faster. But then I'm moving even faster, so I can cover more distance in the same time interval. If I'm moving even faster, covering more distance in the same time interval, it looks like a curve if I was to plot the points. So, long story short, if you see a curve on the position graph, I am speeding up, I have an acceleration. And the rest I've explained there. Now, more graphs, same thing, let's go through them. Position is a straight line going up a little. That means it is changing its position, which means I have a speed. It is having a speed, a constant positive velocity. It's going up. There is a rise and a run. I can calculate the slope. We have a speed. B, this is going upwards, which is towards the positive side. It's going towards the positive side, so the velocity, you can see, is getting faster. Remember, the curve. The velocity is increasing, meaning it is changing its velocity. It has an acceleration. So that's what you can say along here. You can say either of the two things. Next, let's look at C. C is going up, but look, it's going up at a straight line. It's a steady pace. So you could say it's positive. You can also say it is constant velocity. Constant positive velocity. Okay. At rest. Now, D is saying it is at rest. Let's see if that makes sense. Well, yes, it does. The speed is not there. Why? That was a perfect line. Look at that. The speed is not there. Why? Because the position didn't change across the time. He stayed in the same place. I'm going to keep that there because that was a perfect line. E, negative velocity. What is it talking about? Right here. It is going towards the negative side, passing through the origin. That was not perfect. I got lucky then, didn't I? This is going that way, to the negative side. You might think it's slowing down, stopping, speeding up. No, that was the velocity graph. This is as equivalent of me if I was going left to right. If I was having a zero position here, someone standing over here at the zero position, the origin, and somebody is over here, all he is doing for E is he is going past this person, and then he is going further on to the negative side, into the final position on the left. Why does he have four arms? I don't know. That's what's happening here. So hopefully that makes a little bit more sense now. Over here now, we're talking about deceleration, acceleration. Let's see what's going on over here. So this is a position graph again. It's curving, so there's some sort of acceleration going on, and it's going downwards. So it is negative. It is negative, so we have a negative velocity, and it is changing its speed. It is changing its speed, so we can say it is accelerating. So there is a, technically you can say it is decelerating, so it is changing its speed. And slowing down, well, it is slowing down. No, it's not slowing down, it's getting faster. It is not slowing down. If you look at the graph, this, let me get rid of the line. As the time goes on, the slope gets bigger, bigger, bigger. It is actually getting faster towards the origin. So again, this is the origin position. This is on the positive side. So maybe somebody, there's that guy standing in the middle again. There's a guy to the right, and he sees him, and he says, ready, set, go. He runs, and he gets faster and faster and faster, and he gets to him for whatever reason. Maybe he had a bag of Cheetos, I don't know. So that's speeding up. Slowing down would have been something like this. That's slowing down. So keep that in mind. So in this case, only 1 and 3 would be correct. Very nice. Now, let's get on with the rest of these graphs before we move on to the freefall stuff. Here are position time graphs again, which is positive acceleration. Remember, for acceleration, the position graph makes a curve. The position graph curves, the velocity graph is a straight line. So position graph curving, that's the only one here, B. This is accelerating, getting faster. This is not moving, at rest. This is constant speed. And this is decelerating, slowing down, and eventually he will stop in a straight line. So that's why B is the best one over here. Next, moving positive velocity and negative acceleration. I've kind of just said it. It's positive because it's going on the positive side, and slowing down. From the previous video, positive and slowing down, they are in opposite directions. So the velocity is positive, the acceleration is negative, which is not correct for this one over here. Well, let's see. It's going to the negative. Okay, fine. It's going to the negative. So that's correct. It's asking for which one's not correct. So this is good. Acceleration, well, looks like he is slowing down. No, he's not. He's speeding up, but he's speeding up in the negative side. Acceleration is getting more in the negative side. So that is a negative acceleration. That's why this is wrong. Positive, the acceleration would be upwards, opposite of the speed and the position, which means it will be curving the other way. It curved like that. That means the acceleration is upwards. Magnitude of the velocity is increasing. Yes, it's getting faster and faster as the distance goes. Acceleration and velocity cannot be in the same direction because we've agreed that the velocity... No, it can be in the same direction. Sorry, this graph, it is the same direction. It is moving downwards, getting faster downwards. So yes, the acceleration is down. The velocity is also down. They are in the same direction. The only incorrect option we have is B. And I think that's everything done over here, and that will keep it nice and short and sweet. Perhaps I'll make a start on this one here, just to start off a little bit on the freefall. A ball is thrown upwards Where does it have a zero velocity and a non-zero acceleration? So you have to understand what's happening. As I throw the ball up, I will have an initial velocity in the upwards direction, but it's getting slower, 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 stops mid-air for a brief nanosecond, and gets faster, faster, faster downwards. Acceleration throughout the whole journey is going to be negative. The acceleration is always pointing down thanks to gravity. Gravity is always down everywhere. The speed is positive, slowing down, stops, v equals 0, speeds up in the negative on the way down. Fun fact, the positive value here will be equal to the negative value in the exact same location. On its way up, maybe it's +5. On the way down, in the same spot, -5. Maybe we'll use that later. I don't know. So now we can say zero velocity, non-zero acceleration, Q. Question 2, thrown upwards, acceleration at the highest point. We already know that. Acceleration is always negative, always down. A little trick. The velocity at the highest point will be 0, but not the acceleration. Okay, let's go to this one here. Piece of chalk is thrown, positive of course is upwards, negative is downwards. The position, what is it saying? What are the signs of the position, velocity and acceleration upwards? Kind of mentioned it here. Upwards, in the upwards motion, the V will be positive, fine. And the position is going upwards, so that is, he's landing over here. The starting position was here. It is also positive, upwards. So that was the velocity, that was the position. They're both positive. But remember, acceleration, what's it doing? It's pushing down all the time. Acceleration is always negative. It ruled out this one straight away because that said acceleration is positive. The position, it was not at the bottom, it went up. That's why this one is wrong. And over here, both of these are wrong. This one would have been fine. The best answer is A. Upwards, positive position, positive velocity, and negative acceleration. Okay, so done that one. We're over here. What is the velocity and acceleration at the highest point? Just like before, velocity at the top is 0, acceleration is negative. Negative gravity. Remember, gravity is the thing pulling it down, minus g. When is a ball's velocity 0? Said it already, highest point. On the way up is positive, halfway down is negative, just before is also negative, and that's it. The ball's acceleration, when it reaches its highest point, same thing, it is going to be negative. Okay, I'm going to stop this video there and then continue in the next video.